Hello everyone, welcome to my programming club. Today we will be solving another daily Leetcode problem, and the problem's name is sum of subarray minimums. So you are given an array of integer and you have to find the sum of minimum of each subarray of the given array. So let's say this is the array given to you, then these will be the subarrays that can be generated from the above array. A subarray is a contiguous part of array. Okay, so it can be a subarray 1 2, it can also be a subarray, but 3 and 2 cannot be a subarray since they are not contiguous. We are missing one in between. Okay, so this is what a subarray is, and among all the subarrays you have to return minimum. For example, minimum of this particular subarray is 3 since it is having only one element. All of these are having only one element only, so their element are written as it is. Now when the subarray is having more than one element, we will be picking minimum element from that subarray. So minimum from 3 colon 1 is 1, 1 colon 2 is also 1, and then 2 colon 4 is 2, 3 1 and 2, among these three it is 1, 1 2 and 4 it is 1, 3 1 2 4 it is 1. So if you sum all these numbers, then you will get 17. So this is what you have to return. Now let's have a look at the constants. So the length of the array will be of order 10 raised to power 4, 3 into 10 raised to power 4, and the elements in the array are ranging from 1 to 3 into 10 raised to power 4. So how to solve this particular problem? Let's take the first example. To understand or do some observations, how we will be coming with the approach. So let's say this is the given array to you, then you have to return sum of minimum of all the subarrays that this particular one is having. So instead of forming the subarrays, let's say we want to use a brute force approach, and we want to form all the subarrays. And then pick minimum from them. Now even to form the subarrays, what you will be requiring is you will be using two nested loops. One will be for the very left index of the subarray. Let's say you pick this subarray. One will be for this left index and another will be for right one. So you will be requiring at least order of n square operations, where n is the size of the given array. This is the array that is given to you. So in total these number of operations will be required, and since n here is of the range, at max it can be 3 into 10 raised to power 4, so it will be nothing but 3 into 10 raised to power 4 whole square, and it will be 10 raised to power 8 into 9. So these number of operations will be required even for generating subarrays, let alone the part where we are picking minimum from them. Okay, even if we put aside this part, even for generating subarrays, this much number of operations will be required. to generate all subarrays. And these number of operations exceeds the number of operations that are allowed in 1 second. There is an operation limit. Basically, if the number of operations required by your program to solve the problem exceeds or become equal to this limit, then your solution may not be accepted and you will getting a TLE, time limit exceeded, and you will not be getting IAC, accepted solution. Okay, so in order to get accepted solution, what you have to do is you have to optimize this approach. So this was one way of looking at the approach to solve this particular problem. Let's try another way. Here what we will be doing is, instead of generating every subarray, let's say this is the array given to you. Instead of generating every subarray, we will be taking each element one by one, and we will be seeing how many times this element can be minimum element in all the subarrays included. So let me write it for clarity also. For each element, we will see how many times that element can be minimum element in all subarrays possible. For current array, so let's say we are to decide how many times one will be appearing as minimum element. Okay, so let's bring all the subarrays of this particular array to our digital board. So these are the subarrays that are there. Let me zoom out. I think this should be fine. Yeah, it's fine now. Let me zoom in a little bit. Yeah, this should do. So how many times one is appearing? 1, 2, 3, 4, 5, 6. In all these subarrays, one will be the minimum element. Okay, so it is appearing 6 times. So one is contributing 6 times to the overall sum. Let's say we have to return some variable total sum. Then one will be contributing 6 times. One will be contributing 1 into 6. Okay, this is the number of occurrences of 1 as minimum element. Okay, so we are interested only in the number of occurrences of each element as minimum element. Okay, this is what we are interested in. So how to find this particular thing out? So what we will do, let's say instead of 1, well, let's say for simplicity, and right now you are picking 1. So how many elements on the left are there that are bigger than 1? The number of elements that are bigger than 1 are bigger than or let's say equal to n for now, for 1, equal to 1 or bigger than 1. This is what we are looking for on each side. Okay, so 3, 2 and 4. So on left side, the number of elements that are bigger than 1 are 1 if you exclude 1, and on right side the number of elements that are bigger than 1 are 2. Okay, so if you have to form subarrays including 1, then how many number of subarrays can be formed? That's the question. So if we have to merge this left part with right part including 1, how many number of times how many number of subarrays can be there? So the number of subarrays then can be there can be easily find out if you multiply left into right. Okay, that will be 2. So what will be those subarrays? 3, 1, 2 and 3, 1, 2, 4. Okay, these will be the number of subarrays if you want to include both left and right parts. Okay, and if let's say I do not wish to include left part, only right part I want to include with 1, then how many number of subarrays can be there? This was when you were including both left and right part. And if you were to include only plus 1, only right part plus 1, then how many number of subarrays can be there? They can be 1 to 4 and 1 colon 2. These two are only there, so it will be equal to right. Then let's say if you were to include only left part plus 1, then how many number of subarrays can be there? Number of subarrays that can be there are only equal to left, so the only subarray that can be there is 3 colon 1 if you were to ignore the right part entirely and just include the elements in right and 1. So in total how many number of subarrays that are there that can be there? And if let's say you neither include left nor include right, only 1, then there can be only one subarray which is of size 1, which is 1 itself. So in total there are left plus right plus left into right plus 1. 1 is for 1 only. It will be subarray of size 1. So this is left part only, this is right part only, this is both left and right including 1. 1 is always included. Okay, and this is 1 only. So this is we are having a kind of a formula here. Let me quickly take it to another slide. So what's the formula? Left size you can say plus right size plus left into right. I forgot to add size here, and then 1. So this will be the number of times that 1 will be repeated. Let's call it times. So this is the formula we are looking for. That we will give us the number of times a element will occur as minimum element in all the subarrays. Number of times an element will occur as minimum element in all subarrays. So this is indeed what we are looking for, but there is a little mistake here that we did. Let's say instead of this particular example, you were having something like this. Okay, let's say this is the input array that is given to you. Let me write clearly here: 71, 55, then comes 82, and then again comes 55. Okay, so let's say you want to write all the subarrays present. While writing all the subarrays, I am not sure whether I have written all the subarrays or not, but the thing which I have shown, which I want to show you, is surely written here. So let's say these are the subarrays that you are generating. So let's say you generate a subarray by including only left part. So this is left part only, plus the number, left part plus number, and let's say the number here was 55. So as you can see, 55 will be minimum in this particular subarray. Okay, and let's say when you were at this 55, you were also generating one subarray that was having only right part plus number. So as you can see, at two different instances you are generating the same subarray. So same subarray is counted twice in your calculations. Okay, so contribution of same subarray is counted twice, and the minimum element will also be same. It will be 55. So as you can see here, you are counting the same subarray twice. So in order to avoid that, you have to do some changes here. I will show you the changes in the implementation part. You have just to make sure that you are doing counting of each subarray contribution only once. Okay, so this subarray was having 55 as the minimum element, and it was counted twice because of our scheme of left and right only. So what is happening is, this part of the formula, left size plus number and right size plus number, this part of the formula is causing us to count contributions of a subarray more than once. Causing us to count contributions of a subarray more than once. Okay, I think you understand. I think there is no need to write again and again. So this is the part that we have to take care while we are doing the implementation, this part. So let's see how we'll be implementing this particular thing. Firstly, before proceeding with the implementation, the concept of next greater element, or say previous greater element, or this is just an application. What the concept is, the concept is monotonic stack. You should be familiar with this particular, you can say it's not a data structure, you can say it's indeed stack only, but we are using stack in such a way that we will either be having a decreasing order or increasing order of elements. Monotonic means it will be either increasing or decreasing. Whether it's strictly increasing or strictly decreasing, that's another case, but it will be following some order. Let's say stack is something like this, 2 1 and 0. So this is, if you say in this way, monotonic decreasing stack. And let's say this is something like this, 1 2 and 3, not like this, 3 2 and 1. So if you go in this direction, the stack is monotonically increasing in this direction. Okay, so whether we are considering strictly increasing or strictly decreasing, that's a different case altogether, but this is what monotonic stack is. So we will be using stack here to get what, let's say the element of index, the index of element, sorry, index of element which is lesser than 1. So 1 was considered in this particular example. So there is no element on left that is less than 1. So you will be returning -1 here, and on left side of 1, and index of element which is lesser than 1 on right side of 1. So there is no element which is, you know, on right side of 1 and is smaller than 1. So what you will be returning, you will be returning the length of this particular array, since there is no element there. So you will be returning the length. Okay, or let's see, for the sake of consistency, what we are returning in the code. Yeah, we are returning length indeed. So why we are choosing to return -1 and length, I'll tell you during the implementation that I will be showing. So this will give you left size and this will give you right size. Now since this particular part was leading us to count contributions of one subarray more than once, so we will be inserting equality condition in either of these two, either in right size calculation or left size calculation. We will be considering equality condition. So let's say we put here which are lesser than or equal to, and this is strictly lesser than. Okay, all the elements that are strictly lesser than and all the elements that are either less than or equal to 1. So if the input array would have been like this, then if let's say you were to decide for this particular one, then you would have stopped here only, since it is the element that is less than or equal to 1. So, and for the right part you will be, let's say there is 1 also, continuing till the very end of the array. You can have other way around also. You can stop here and continue till the very end on the left side, but that totally up to you. It will not change the result of the calculations. Okay, so why we are doing so? because it was leading us to count the contributions of a single array more than once. So this will surely stop you from counting contributions of same subarray more than once. So let's see the implementation. More things will be clear while you will be seeing the implementation part. If you are still not clear with how we will be implementing these things using stack. So this is the part. The thing that will be required to return is return the minimum. We will be returning minimum subsum. Okay, this is the value that you will be returning. I have just initialized length of your length variable with the length of your array or size of your array, and since we are told us that your answer may be very large, you have to take modulo with respect to 10 raised to power 9 plus 7. So I have taken another variable and initialized it with the value that is mentioned in the problem, and then we will be needing two things for each of them. For each element we will be needing two indices. For each element in the array we will be needing two indices of which are or say that is index of previous lesser element or let's say rename it. We are renaming it to previous lesser or equal. You can use instead of previous lesser, you can make next lesser or equal also, but I am doing it previous, or let's say just to show you I will change the code a little bit. Instead of next lesser it will be I don't know why the shortcut is not working. Yeah, it's working now. So next lesser or equal index. I think it will be very long name, so we will be keeping it to equal only. So let's change. So you see it is changed, and instead of equality here we are inserting equality in this particular condition. Let's see whether I will be explaining. Let's first of all let's see whether it's working out fine or not. Yeah, it's working out just fine. So there is no at least syntactual errors in the code. So what we are doing here is index of previous lesser element we will be requiring for each element, and another index that we will be requiring is index of next lesser or equal element. Why we are using why we are requiring these two values? Just to get the value of these two, left size and right size. These two we are to calculate, we have to calculate. So that's why we are needing the index of previous lesser and next lesser or equal. So this stack will help us. How it will be helping us? This is just a standard implementation of monotonic stack. If you go over the internet and search monotonic stack, okay, I will be providing link of this particular article. Here are some applications also of monotonic stack. So you can check this article out, and then you will surely be able to understand what monotonic stack is and what are its applications. Okay, so basically what are you doing is, let's say you are using stack. I will be explaining for the left part only for now. Let's say the stack was initially empty, so you put index of this particular element. These are the indices, so you put 0. Now you are at 1. You will be seeing that whether this 1 is less than the element whose index is present in the stack at the top. So the element at this particular index is 3, and indeed 1 is less than 3. So what you will do, you will just pop it out, pop this index, and instead of that you will be pushing. You will keep popping out till 1 is lesser than the element present at the top of the stack, whose index is present at the top of the stack. So you will be at last pushing 1 till the stack becomes empty. Okay, so 1 is the index of 1. If let's say your stack would have been something like this, let's say here another variable was there, another number was there. For the sake of simplicity, I am taking it -1. Okay, so this is the array that we were considering earlier. This is the -1 index, and let's say there was some other number that was present here. Let's say it was 0. Okay, so this was -1, and then there was 0, and you were considering for 1. So 1 was surely greater than the element present at this particular index, so you popped this element out. Okay, now you came to this particular index. Although it's not a valid index in zero based indexing, but still we are considering it just for the sake of consistency. At -1, 0 is present, and 1 is not lesser than that. So you will not be popping this element out, you will be stopping your popping operation here only, and you will be pushing the index of 1, which is 1. So this is what monotonic stack is. All of your elements that will be represented by these indices will be in increasing order. And since you are not considering equality here while considering the previous lesser, you are only considering strictly lesser than, so it will be strictly increasing. Okay, so this is the part for calculating previous lesser. I think this is of no use, so this is part for calculating previous lesser, and this is the part for calculating next lesser or equal. Okay, so the implementation of both parts are pretty much similar, except this little condition here. We are considering equality here. If you want, you can consider equality here instead of there, but that's totally up to you. Okay, so if the stack is empty, you will push the current index. If stack is not empty and the value of the index at the top of the stack and the index that is at the top of the stack, whatever the value that index is representing, if this value is greater than or equal to the current number, then you will be popping that value out, and for all the values that are being popped, current index will be the next lesser or equal index. Okay, this is also a major part of the, you can say, approach here. For all the values, all the indices or say that are popped out, for them current index is next equal or lesser elements index. Okay, so similarly you will be doing for the previous lesser part, just that we are not considering equality here to avoid taking the contributions of one subarray more than once. Let me mention here also, to avoid taking contributions of one subarray more than once, we are skipping out equality condition here. Okay, so and while there are values in the stack, this will indicate that there is no value on the right hand side of those values that is lesser than those values or equal to them, so they will be getting index as length of the array, and on the left part it will be getting -1, since even the 0th value is not lesser than them, so you will be getting -1. Okay, so if you see here, what is the index after 0th index? It is -1. And what is the index after this 3? It will be equal to the length of this array, which is 4, by the way. So that's why we are using these two values, and then you will be simply using our formula that we have just derived. Okay, left size plus right size into plus left size into right size plus 1. So this is the formula that we have just derived, and you will be taking the contributions of the current subarray or current number. Towards our answer. Okay, so these are just debugging statements, you can surely remove them, they are of no use as of now. Okay, and then you will be returning your minimum sum. This is just modular arithmetic, we are taking mod with any value in order to avoid any overflow. Let's submit it once again. Yeah, it's working fine. So this is how we will be solving this particular problem. If you are still having any doubts or any queries in general, please feel free to ask them in the comment section. And for the time complexity and space complexity wise, it will be order of n time complexity, since we are doing a linear traversal of the given array. And space complexity wise also it will be linear. Okay. Since you are using stack here, which will be using n elements, where n is the size of the given array. So thank you for watching. Have a great day ahead.